Welcome everyone to another OCP tap call. This is call number 140. It's my pleasure to introduce today's OCP tap speaker, Yuliang, the initiator and tech lead of Project Firefly at Google. Yuliang joined Google in 2020 after completing his PhD at Harvard and was awarded the prestigious SIGCOMM Doctoral Dissertation Award the same year. He's been an active contributor to the research community, including serving on the SIGCOMM program committee. At Google, Yuliang's current work centers on building next-generation systems powered by precisely synchronized clocks, pushing the boundaries of what's possible in timing-aware computing. Previously, he was a core contributor to Google's Falcon, a high-performance transport protocol, and has published extensively on the topics like clock synchronization, network transport, congestion control, and telemetry in leading conferences such as SIGCOMM, NSDI, and OSDI. We are thrilled to have Yuliang with us today. Please join me in welcoming him.
Thank you, Emma, for the introduction. Okay, so let's get started. Hi, everyone. I'm Yuliang Li. So today I'm going to talk about our project called Firefly, which builds a very scalable and ultra-accurate clock synchronization for data centers. So as we all are familiar with, the demand for a tight clock synchronization accuracy has been growing for years. Initially, right, at the millisecond level, we mainly used clock for maybe logging or getting timestamp for human repurpose. And as we move towards a more performant and more reliable data center network, there are new demands that require looking for microsecond level accuracy. And as more applications such as financial exchange arises, we are looking at 10 nanosecond or even sub 10 nanosecond level accuracy. And this is because in financial exchange, even a very small timing advantage can translate into a very significant financial gain. Right, so that's why they care about a lot the accuracy. So this certainly bring new challenges to achieve sub 10 nanosecond accuracy. So let's start with the very simple building block of clock sync. And from there, I will talk about where those new challenges come from. The clock sync, put in a simple way, is just measuring the offset between pairs of clocks, right? All the protocols such as PDP, NTP, or other clock synchronization, they all build on this, right? Essentially, we get a timestamp of a pair of packets between the two clocks in the forward and backward directions. And with each of these packets, we can compute the offset using one packet. For example, this can be computed by the receiving time of B minus transmit time at A minus the one-way delay. And from the second packet, we can also do a similar calculation. And although we don't know one-way delay, what's the value of it, if they are equal, then adding these two terms together, the two one-way delay cancel off. And then we get this beautiful equation to calculate the offset. And to put it visually, because the offset is the sum of the blue term and the origin term divided by 2, we know the offset is in the middle point of the two values. And these two values, by the way, essentially the distance between these two values to the offset is the one-way delay. As we all know, right, the one-way delay cannot be exactly the same in the two directions because there are asymmetry. For example, the path for the forward packet and the reverse packet can be different. And because of the cable length can also be different by maybe tens or hundreds of meters, the delay can also be different by hundreds of nanoseconds. Right? These are well-known challenges even before we move to the 10 nanosecond accuracy. But with 10 nanosecond accuracy target, we start to face a whole bunch of new challenges that we previously don't care about. For example, there are some solutions to deal with path asymmetry. For example, in the financial exchange world, they use equal length cable, right? Every layer of cable in the network, they buy the them from the using the same nominal length. But even with the cable with same nominal length, they can still have a total of tens of nanosecond difference across a path, because the cable length can still have some tolerance, right? They are not exactly the same. They can have maybe around 1% of difference. And beyond that, we start also start to care about the component asymmetry, right? That is, the delay of the same hardware component is asymmetric in the two directions, traversing them. For example, one of the major sources is the optical transceiver, which can introduce up to 10 nanoseconds of asymmetry per module, right? So summing up over the path, it can be large, and it can be a significant challenge to sub-10 nanosecond sync. Beyond the asymmetry, the second source of error is jitter, right? We all know the queuing delay can cause jitter, 10 to 100 microsecond jitter. And there are some solutions to them, right? For example, we can use transparent clock, but remember, transparent clock, it also uses the switch timestamps in the switch, which come with timestamping jitter at hardware. And timestamping jitter, both the switch and the NIC, they can have up to 10 nanoseconds per timestamp. And the more switches we involve, the more timestamp it involves. Alternatively, if we use strict prioritization of packets to bypass the queues, it still cannot get rid of the queuing delay, because a sync packet cannot preempt an already transmitting packet. So the packet arrives, it will be the next to send, but the one is already sending, you cannot bypass that. So that introduces jitter as well. And the third type of well-known error source of clock sync is drift, which also becomes more challenging when we're targeting sub-10 nanosecond accuracy. Previously, we know oscillator major part of the drift come from the static drift, which can be tens of ppm. And those can be measured and compensated. But when we are targeting sub-10 nanosecond accuracy, we also start to have to be very, very careful in handling the dynamic drift, because the oscillator frequency or its rate can change a lot, right, when we're targeting 10 nanoseconds in just 1 second. So beyond the three common error sources, now all becomes harder to solve when targeting sub-10 nanosecond accuracy. We also have to look at the source of time itself, the time server. And time server itself has some error, which were previously not so significant. But when we're targeting sub-10 nanosecond accuracy, they start to become very important to handle. A common time server, they typically has antenna, which get GPS signal from a satellite and transfer the time to atomic clock, atomic oscillator. Right? The transmission may have tens or 100 nanosecond error because of the discipline between them. And more importantly, from the atomic oscillator to the CPU and from CPU to NIC, they all involve PCIe, which have microsecond jitter. And these are very hard to bypass. Right? Unless you have a 1 PPS out of NIC that directly connect to the atomic oscillator, you cannot bypass the PCIe jitter. And we want to build a system that is generic to all the scenarios. So we have to deal with these time sources, which themselves could have tens, hundreds, or even microsecond level accuracy, hundreds of nanosecond or even microsecond level accuracy. The third type of challenge comes from the scalability, which becomes significantly more challenging when we're targeting sub-10 nanosecond accuracy. Existing solutions, they typically use a centralized architecture. For example, PDP, the root talk to all the leaves, right? Or it's a slowest, but it's still like a one-to-all root to the other things. Or in Huygens, it's a controller that talks to all the different leaves, tell them how much adjustment they have to make. Because of this centralized architecture and its scalability challenge, they have to limit the synchronization interval. It cannot run very frequently because of bottleneck. And therefore, it also requires highly stable oscillator to keep the dynamic drift during those sync interval very small. Right? If we're targeting sub-10 nanosecond accuracy, then the drift of the oscillator itself cannot be more than that during that long interval. And in addition, the failure of the centralized component also can disrupt the synchronization of all clocks. So in order to address these scalability challenges, there are alternative architectures such as tree architecture used in PDP boundary clock mode. This improves the scalability in normal case, but also brings new challenges in the failure or corner cases because it introduces more dependency on the layers in the between. For example, if there is some boundary clock in the middle that has an unstable oscillator or even misbehaviors, right, or it is drifting, it cascades to all the downstream clocks. And the failure of any single boundary clock also disrupts the synchronization of all downstream clocks, of course. So to summarize the challenges that we've talked about, there are three key challenges we are facing. The first is that we have to look at the new error sources. Actually, it's not new error sources. It had been there, but we previously ignored when we are targeting lower accuracy. But when we started targeting 10 nanosecond, we have to consider them, including all the asymmetry, drift, and the jitter. The second type is a time server error, which could have hundreds of nanoseconds to microsecond, and the scalability challenge because more challenging at sub-10 nanosecond accuracy. So what made it possible to address all these challenges with Firefly? Here are the three key insights of Firefly that we built in order to address them one by one. The first, which I think is the most important one, is the consensus. So instead of letting clock running in a leader-follower mode, which we build a tree, right? In Firefly, we build a consensus graph. So in the graph, every node, every clock talks to multiple other clocks in the network, right? We use a random graph. So by doing this consensus, it gives us additional opportunity to reduce the error. So instead of just following your parent and have to accept all the errors associated with that parent, right? All the asymmetry drift of the parent and jitter with that. Now we have multiple other peers that we can average from. So these errors are largely independent and can be, when doing average, they become smaller. So that's how we can get the accuracy even smaller. The second insight is that we decouple the internal and external sync in a way that the consensus is the major force that to keep all the clocks closely, tightly synchronized together. And well, all the clocks, they also periodically talk to a time server, right, in a longer time interval. It's the time server gently pulls the consensus towards the time server. And third insight is how we address scalability, right? By using the consensus, we actually turn the scale in favor of clock sync. This is because with more clocks, we have more opportunity to do the consensus and average out those independent errors. And also with more clocks, it leads to a more stable consensus. Imagine the consensus of 2 clocks versus the consensus of maybe 1,000 clocks. The 1,000 clock consensus is certainly more stable than the 2 clock consensus. And this property in turn benefits the external sync and also internal sync. So we have saw the logical view, and when mapped onto the physical network, right, like this. So here's the system view of the Firefly. All the NICs, they talk to each other in overlay random graph. And all NICs, they all periodically talk to a time server in a lower frequency. By the way, it doesn't have to do on the NIC. If you want to synchronize all the switches, you can run Firefly on the switch as well. And you can still form a random graph over there. And we have proof that with this consensus graph choice, each NIC probe D random other NICs. And the D only need to be proportional to log n, meaning the scalability is log n scalability. We have proof in our SIGCOMM paper. And here is the synchronization process, a high-level overview of it. With the initially all the clocks, they are separated, right? They are not synchronized. The blue dots are all the NICs, and the red boxes are the time servers. With internal sync, all the NICs, they come close to each other, very closely and very tightly. And as they all talk into a time server, right, they gradually move to a time server. And the whole swarm of NIC, they move as an entirety towards the time server. So this is how we achieve the very tight internal sync, right, on the sub-10 nanosecond NIC-to-NIC accuracy, while still move towards the UTC. And as we have shown in the paper, it's also benefit the external sync as well, because the stable internal consensus makes it easier to filter the error from the time server. So I would like to encourage everyone to look out for our SIGCOMM 25 paper and presentation, which will happen on September 9th. In that paper, we have provided theoretical foundation, including proof of scalability, proof of convergence, and proof of bound on static error. We also have evaluation results that showing sub-10 nanosecond accuracy with 1 PPS measurement. It also shows that it's more accurate than normal PDP and Huygens, and the resilience to asymmetry, jitter, and drift. We also evaluate its scalability and its tolerance to time server errors. So please stay tuned for our SIGCOMM paper and the presentation on September. Thank you.
Thank you for the presentation. Okay, let's open the floor for questions.
I'm Bob with a question.
Hey, Bob.
Is the communication between clocks unicast or multicast?
Unicast.
I have a question about the hardware setup and reproducibility. So the PPS measurement showing less than 10 nanoseconds, I mean, most NICs have like 8 nanosecond quanta or something like that. So what kind of NIC requirements were necessary to reach this 10 nanoseconds? And then also maybe a secondary question or a parallel question is what kind of like utilities are available to reproduce this kind of test setup? Like if we had a small scale lab setup, is there like a PTP4L equivalent that uses this algorithm that's easily testable?
Yeah, thanks for the question. For your first question, we actually tested various scenarios by injecting even more different error sources, such as the asymmetry, drift, and the jitters. And we showed resilience to all these error sources. Regarding to your question about the NIC quantizations, because we are using consensus, right? Although individual NIC, they may have large quantization error, it will average out. So when one NIC talk to multiple others and take average of them, right? Even individual peer, they may have maybe 8 nanoseconds as you mentioned, this will average out. So the sync itself will be lower than the effect of the 8 nanosecond quantization error you mentioned will be lower than 8.
I just meant that the NICs themselves, right? The 1 PPS accuracy can only be adjusted more or less to like 8 nanoseconds. So pretty much no matter what you do, you'll probably have plus minus 8 nanoseconds PPS variation, even if you have incredibly tight sync, no matter the algorithm, more or less a hardware limitation. So is that what you saw, or are you using NICs with higher granularity PTP frequency, or?
Maybe also add to this, are you using hardware timestamping or it's not? Because I mean...
The packets use hardware timestamping. The 1 PPS certainly doesn't use packet timestamping. It's a separate 1 PPS channel. Yeah.
And then your network is PTP aware, I'm assuming.
Yes.
So you have basically... so, I mean, in other words, Firefly is a servo that runs on PTP.
You can think of it as not only I'm not sure what's the definition of servo here, but I think
it's a software that runs basically on the servers that handles that's what we call. I mean, of course, you know, I'm just like syncing my nomenclature with you. I'm not going to teach you.
Yeah, sure, yeah. It's a new algorithm running on the server, and yeah, it will benefit from the transparent cloud in network. Yeah.
Right.
So therefore, it's using packets formatted as PTP?
Yes. Although we just use the PTP format to get the benefit of switch transparent cloud.
Hardware timestamping, yes.
What about the software utilities? That was my second question, was like if we wanted to reproduce this test setup with NICs that we have, is that part of the SIGCOMM paper? Will you be releasing any open source like utilities to demo this or something?
Yeah, in our SIGCOMM paper, we have all the design details. So yeah, regarding the software, that one we have to explore internally, yeah, before we release it. If internal there's a consensus to release it, we will release it.
Oh, I see. So the algorithm is described in principle, but the actual code implementation isn't planned to be released at the same time.
Yeah, not yet.
I see. Okay.
So Yuliang, there is like this general question that comes up, and perhaps this is what also Bob was referring to, and that is the precision, and that's also what Julian also refers to. The precision that you have from in a measurement can never improve with an algorithm. And yeah, even if you have like multiple measurements or measurements in parallel, like what do you call it? Like I forgot the term for it. Like quorums or things like this.
Yeah.
You always are bounded by the precision of perhaps the worst, because that one will introduce, and I mean, the mathematical term for it in stochastic system is the Kramer-Rao lower bound, which basically is from the curvature of your PDF. And so if, let's say, your timestamper's granularity is, let's say, 8 nanosecond, well, there's no way you can go below that. Like, for example, this is another problem I have with these software-based methods, that they claim they go in nanosecond world, while they basically say, oh, PTP is bad and we do things just with software. And then when you look at software, okay, what's the precision that you have with a software timestamp? You're in the milliseconds world. So of course you can always show things, like, do the math and like use like, I don't know, some interpolation, and then say like, okay, these two go through together, and then divide all of them. When you're basically violating some of the measurement principles when you then just look at the numeric number and say, like, look, this is in nanoseconds, you know? So a good way, and I really look forward to see your paper, a good way for especially this community, speaking on behalf of this community, is always checking the PPS signal coming out of the things, let's say, versus a reference that you look at all of this and you look at, like, let's say, a certain time and look at the RMS and then say, like, okay, this is the error that you get ultimate. And if you just go consensus-based, which you were mentioning, it will be also bounded by the latency, because that follows like the Cal theory. Then you cannot basically see anything less than the latency. You may perceive it, you know, great, but the latency is now obscuring, you know, like the high precision. I'll give it back to you. Sorry.
Yeah. I think these are great questions. So regarding your first question, we are measuring the accuracy using 1 PPS, right? It's just measuring. And you are saying when doing the synchronization is separate from measurement, right? The synchronization, they do have the timestamping jitter or timestamping inaccuracy. My understanding is that, so let's, for example, we take 2 clocks as an example, right? Some packet may have jitter of +5, some packet may have jitter of -5, -4. Over a number of packets, they will average out down to maybe 2 or 1 nanosecond accuracy. That's how the average or the consensus help improve the accuracy, right? Even if all the
True. That's basically, you're basically going through like central limit theory. When you have a lot of them, they average out and the average will go in the middle. Sure. But that still doesn't allow you to claim higher precision.
Yeah, our claim is not based on the synchronization itself. Our claim is based on the 1 PPS measurement that's completely separate from the software.
Can we drill into that? That might help, because I can envision 2 different ways that you could make such a measurement. One would be that you have a reference PPS, perhaps the one that, you know, came directly from the GNSS clocks, and you feed it into one of the hosts, and you take timestamps on that 1 PPS input to the host. The other approach I can think of is that you take one of the hosts, which is part of the consensus, and you produce a hardware output from that host, which is a 1 PPS edge, and then you use an instrument like a time interval counter to measure the difference between your reference pulse and the output from the cluster. So rather, the question here is, in what domain did you measure your difference from PPS, inside the host or externally on an instrument?
Yeah, thanks for the clarification. So we take the PPS out from the NIC, from multiple NICs, connect to oscilloscope. So using the oscilloscope to compare all these different NICs, their signal, right, how well they are aligned up. Yeah.
I've got a question. Would it be better to use the NIC PPS or a PPS from, say, a time-aware GPIO?
Using a PPS from GPIO. Sorry, what do you mean?
Do you know the time-aware GPIO? Time-sensitive networking. It's an Intel thing. There's a description on the wiki for this group, for the Open Compute TAP group. Some motherboards have a PPS signal coming right off the system clock. So that would give you the system clock accuracy as opposed to the NIC accuracy. Now, if you're using hardware timestamps, the NIC accuracy, I don't know, it may be better. Bob, you probably know more than I do about that, but there are 2 different clocks and 2 different measurements. And if you're doing the servo and stuff on the main processor, the system clock may be better.
Yeah, we are synchronizing the NIC clock, so we are using the 1 PPS from the NIC. Yeah, but I think, yeah, your suggestion is a great one in the future, that once we synchronize the system clock to the NIC clock, we can use that GPIO to measure system clock accuracy as well.
Now the other thing is, it looked like you're doing a lot of the work inside the processor. Are you taking into account application layer error?
You mean the software error in the Firefly software itself?
Not exactly. Stack Research has a great blog. It's about 8 or 9 pages on application layer error, or ALE. It's a great read. And what they found is the configuration of the server can make a huge difference. I don't even want to try and describe this blog. It's great. It's a great read, but every server I've seen has a slightly different application level error, which is really, it's just how quickly can you read the system clock and get a response back. And it's not always, there's a lot of things that go in there, like interrupts and stuff, but if you look at the minimum number, it can vary quite a bit. And it depends not just on the model of the processor, the rest of the load on the processor, the heat because of the turbo mode. Everything we know about timing, of course, affects it. And this is just one more thing. Some clients will take it into account, some clients will not take it into account. But the thing is, if it varies, if all your servers are each a little bit off, then you're going to be having that little bit of error in your calculations that maybe you should be accounting for.
Yeah, I think you raised a great question. So in my mental model, so in the software, right, the input to the software are the packet timestamps, the timestamp of the sync packets. So that is timestamp right at when the packet leave or arrive at the NIC.
Okay.
Yeah, we don't directly read the NIC to synchronize the clock. That's not used. That's not used for synchronization. The synchronization only used on packet timestamps. So,
where do you do the work for Firefly? Is that on the main processor or on the NIC?
It's in core. It's a software.
In the core.
Yeah.
Yeah. Well, there's FPGAs and
it's not FPGA, right? It's a CPU core. Yeah.
Yeah. Okay. So you do it in the CPU. So the time to read the system clock could affect some of your measurements. You'd have to, I don't know anything about your algorithm, so I can't say, but it does affect some things.
Yeah. So the way the some delay affected is after the packet get a timestamp, arrive in our software, and our software respond to it and do adjustment to the clock. Right. This control loop has its own delay, and which can be microsecond level because it's in the software. But in our experience, this microsecond level delay is not that significant because within a few microseconds, the drift is very, very small.
Well, and if I understand your design correctly, the outbound timestamp is also taken on the NIC clock.
Correct.
So the amount of time that it took the software to respond to the stimulus from the network and create the next packet going out on the network doesn't matter because you've effectively used the PHC on the NIC, the clock on the NIC, as a transfer standard. And not the system clock could be set to 1969.
So who's setting the NIC clock?
The Firefly software is setting the clock.
Yeah, Carl, it is basically sorry, Hank. It's basically similar to how the Yocto, from my assuming, that's why I said I call it a servo, right? It basically takes the timestamps and then it reacts on some, like for example, in the classic one, you have the PI controller. This one does something else and then adjusts. This is what I'm understanding.
Okay. So how many packets per second to each other endpoint do you use?
Right now we run 100 of packets per second.
Oh, wow.
And how big are those packets? Just regular PTP sync and?
Yeah, those are small packets. Yeah, it's just try to run sync information.
Have you run any tests to see how the ability to deal with drift varies based on the packet rate?
Drift rate vary with packet rate. Yeah, we did have tests to try to inject different drift rate, right, by randomly injecting some drift to the oscillator. We didn't vary that much on the packet rate because I think currently we're setting the 100 packets in a way that is already very conservative. So I think it's a good question, right? If we lower the packet rate, what's the accuracy can achieve with regard to different level of drift? Yeah.
Yes. I mean, to me, the incentive you have to increase the packet rate is to catch short-term drift.
Yes.
Right. Okay. So in effect, at 10 milliseconds between packets where you are now, you could catch drift at the 10 millisecond level, but not at the 1 millisecond level. Which, you know, I don't think there's a lot of drift down there that you'd be able to correct for. So,
yeah.
Well, how about how do you handle microbursts and other congestion?
Microbursts will affect clock sync in terms of queuing delay. We have the transparent clock in the switch that will tell us what's the total extra delay from the queuing. So we can subtract them out. And of course, we know the transparent clock will have its own error, such as the jitter, or even if it's a long delay, right? The switch oscillator is not synchronized, they have some drift. And this is how the consensus also helps here, where all different, maybe tens of different switch transparent clock, they get averaged out. So it's also smaller.
Have you tried different switches? Because I've seen some 5 years ago, most of the transparent clocks and all of the boundary clocks were hurting time sync. Nowadays they may have gotten better. I don't know. There was only one transparent clock that actually made things better.
We didn't test a very old transparent clock. I think it's a very good exercise to test. Yeah.
I don't know what the new ones do, but I suspect each switch has its own characteristics. We know the ports are all different latencies.
Sorry, what have different latencies?
The ports on the switch.
Yeah. Right. And that should be compensated by the transparent clock. Because transparent clock is effectively is enter timestamp and exit timestamp. So it covers the thing in the middle.
Okay. Can you maybe share the hardware that was used to evaluate Firefly, or at least I think it was mentioned before, but what was the clock resolution on the NIC?
Clock resolution on the NIC? By resolution, you mean the timestamping resolution? It's 1 nanosecond.
Yes. I mean, timestamp resolution, I mean, when the NIC clock is stepping by 1 step, how much nanosecond is 1 step?
Yeah, the timestamping is 1 nanosecond resolution. Yeah, although the frequency of the oscillator may be different. So, yeah, I have to check internally. I discuss.
He might mean what's the granularity, what's the smallest interval you can measure, as opposed to how many bits do you have in the word to, you know, say this is 1 nanosecond or this is 1 picosecond.
Yeah, agree. Yeah, this is what I mean. The frequency, right? The hardware clock frequency, meaning how many ticks per second, megahertz. That number I have to check internally before I disclose. Yeah.
Related to that is the question of the serialization speed of the Ethernet. Would it be 1 gigabit or 10 gigabits or something else?
In the network, we use 100 gig.
100 gig.
And your switches are all 100 gig?
Switches are, I mean, switch port in the middle of network is certainly higher than that.
So transparent clocks running at 100 gig. I haven't heard of those before. That's cool.
No, they are like I mean, I mean, when I was in Meta, we had like I don't know, all the
Oh,
way to 800. Like it's all Tomahawk. It's all thanks to Broadcom and
yeah.
Cisco and everyone else, and NVIDIA. All of them have transparent clock these days. I mean, thanks
Thank you.
to telco for
Yeah.
pushing the mandate. So then all of the vendors, otherwise vendors will not do anything for you just for fun.
The telecom market is larger. Yes.
Telecom pushed it, and we have basically a transparent clock built into all of these things. There were issues, let's say, for example, with this thing called the gearbox, where you want to change like the speed. And I mean, it got addressed at some point, but then the moment it got addressed, we moved, I mean, Meta. We moved to something newer, so we didn't need to worry about that. But that was also a constant error that was always like, you know, but
Are
of course it is. As a matter of fact, like back when I was in Meta, we had more access to high speed switches that have transparent clocks than low speed, because low speed they were older, and then let's say they didn't have hardware timestamping.
An
And
afterthought.
let's say when we want even like a copper one like that, like let's say I don't know 1 gig or something for the lab to play with. I mean, Julian and I had to make it like from scratch basically.
So were those transparent clocks extra charge or free?
No, it's free.
Yeah, it's in the Tomahawk.
Free. It's a
there.
feature. It's a because it's a. I mean, I wish that someone here was from Broadcom, but I mean, you know that vendors. I mean, Hank, you work for vendors. Vendors, they don't charge you what something is worth. They charge you what they can get away with. So if they can charge you for it, they will charge you. But
I won't
usually,
admit to that.
Sorry,
I won't admit to that, but I won't
yeah,
agree with
you
you
don't have to
either.
admit to it. It's economy, right? So, but the thing is, the usually transparent clock is basically just a flag. You set it off, you set it up like in low end, you just set it up and it works. But then in high end switches, you basically set which port doing what. And boundary clock is a little bit more complex, and basically vendors have an easier way to charge you for, because then they have to give you the servo, and then you have to put like basically in the microserver or something and so on. But that's usually the case. Yeah. I mean, what was it like the one that AMD acquired, the NIC, there was a NIC vendor that
Links.
اعمل لك اي حاجه تكتيكيه كده.
the NIC, there was a NIC that basically was not giving you the hardware timestamping unless you pay them something. So they basically just give you a
Solarflare.
fee. Solarflare. There you
Solarflare
go.
had it, yes.
I mean, I found that ridiculous, you know, like, I mean, that's like, but again, vendors charge you what they can get away with.
How many NICs in a consensus domain do you need, or is there?
It can be any NICs in the network you have. Yeah.
Like your NIC could be connected to many NICs, right? Like where do you stop as a consensus domain?
Oh, good
Like,
question.
do you talk to everybody out there, or you feel enough you have reached enough consensus?
Yeah, so we have proved that the number of, so each NIC only need to talk to O log n, and the total number of NICs in the network, other peers, to remain the same level of consensus accuracy.
Okay.
You mentioned an interest of mine, which is the error between a GPS antenna and the output of your GPS clock.
Mm-hmm.
Have you found a GPS clock that can stay within 10 nanos?
GPS clock stay within 10 nanos?
How about 100 nanos?
I think it definitely exists, but it's definitely not universally available in, I mean, all the network we have. So
we have I mean, he's not here. forgot his name. From Fugro. What's his name? Anyone help me? He will not like it that I forgot his name. Anyways, they have this this product, and then you works on septentrion receivers.
Yes.
And you can easily go to single-digit nanosecond. And yes, we tested it, but you're also limited to the coverage that you have from their satellite, because their satellite is in geo, and you basically have, I mean, you have to always calibrate it, but then once you have the sync, you go I mean, single-digit nanosecond, and yeah, I mean, even with GPS, we have experience like with let's say the new U-blocks, or even some other ones. I forgot Etherware or something. We get single-digit nanosecond with those GPS to GPS. But of course, I mean, you need to have, let's say, a atomic clock there. We make basically GPS DO and wait enough to cover the tau, and then now you're getting like something across. But I agree with you, Liang, like there will be always a error between the two, and that's again first principle of measurement, precision. And again, those who claim they can increase precision, I don't think that's necessarily true, because you're like violating law of information theory. Because
Yes.
precision is directly information. Increasing it, I mean, yeah, you can synthetically go in the middle, but that if you go in the middle, that doesn't mean that was the reality. The reality could have been anything that was in that curvature. And that's why you have to mask the whole thing and say middle plus minus this. And so, I mean, that's the
You
work.
haven't removed the uncertainty. So within a
Always,
consensus,
always.
yeah.
You always have to either give one number and a variance, or give two numbers and say between the two.
And distribution.
Yeah, you always have to give two numbers, basically. Center and
At least.
and sigma, or plus, like center plus sigma, center minus sigma.
Yes. Well, this gets back to the drift rate. You know, you can go 1 sub-second drift, and you know, you can go to millisecond drift, microsecond drift, frequency drift, time drift. Yeah.
And again, in Meta, I mean, I published this in various conferences. In Meta, what we did is we basically put multiple receivers across the data center, and then each one of them, they were coordinating to use a different band and different satellites, so they were trying to be independent. And then the clients, they were able to read at the same time four. It was an option to the clients that wanted higher reliability, and they were taking a window of reading, and they were taking the covariance matrix to look at mathematical independence. Once the mathematical independence with the covariance matrix was shown, you were taking the eigenvalues, and then based on the eigenvalues, you could have seen like basically the contribution, which one to which one. It is an extension of like how Kalman filter works, right? And then, but then we don't do at the end, like I skip the whole like averaging, you just pick the one that has like the lowest variance. And then as long as that one falls within everyone else, and if someone is out of the like with the other ones, that's kind of like set theory, that one gets kicked out, and then you go with the lower thing. I mean, you can go all the way down to when you have two of them agreeing and two are off, you throw the two off. If all four disagree, you basically just say this is the lowest and my reliability is the lowest. And then the reliability was calculated basically by random walk, like basically the probability of two random walks match. If you basically one minus two random walks match, and then you are measuring there. If you have two, if you have three, basically the probability one minus the probability of three random walks match when you go through, and then like when you have four, like basically one minus probability of four random walks match when you're doing the measurement. And that way, when you have like four matching at the same time and they're mathematically independent, the probability of you think it's correct but it's wrong was like way off, like, you know,
12 nines or something, you could have like bet your life on it.
Mhm.
And when it was like, let's say 2, then it was like, less. And we didn't need like 100 messages per second. We're going like 1 message per second. That's how we handled it. But I'm pretty sure there is more, treasure when you dig in like deeper. But I mean, I'm pretty sure also there is another mathematical bound to, like, let's say if you go a certain rate higher, you're not getting anything anymore because you're within the quanta that you're getting like from whatever is going on, like your oscillator or whatever. Like there is always like slippery slope on every end with timing. And making mistakes is so easy because it's gonna go silent and you never find out about it until it's late. I'm glad I don't deal with those things anymore. That was very stressful. Anyways, any more questions?
So just one question. I don't know if you can
Go ahead,
disclose it, but can you maybe talk a little bit about how it is going to use, or what is the use cases for Firefly?
Sure. Yeah, so as I mentioned earlier in the talk, I think the newer use cases such as financial exchange and also the very high performance RDMA congestion control, right? They also can be the use case of Firefly. We build 10 nanoseconds for financial exchange, but of course, all of them can be benefited as well.
Yeah, so for example, RDMA, I mean, what is RDMA? How do you use timing for RDMA?
Yeah, for example,
congestion control or financial exchange or even telemetry are very clear, right? Or the databases.
Yeah, so for example, you can measure the one-way delay, so which give you a very good insight in where the delay is stand. And basically, this can be used in RDMA or any transport, and can be used as a signal for congestion control, right? Whether your congestion is in forward or reverse path. Yeah, similar for the telemetry. Yeah, basically you know which direction. And also, if you run Firefly on the switches, you can also know. Basically, you get more granular timing information along the path of your packet.
Okay, so it's somewhere along telemetry, but telemetry for RDMA?
For RDMA, yeah. I think one use case for RDMA is the telemetry. Yes.
I thought I heard there was some work looking at congestion avoidance with precise timestamps in RDMA, as opposed to congestion control. Like you're trying to coordinate when results are sent towards a central point in a large model with distributed shards coming back towards the center. You try and avoid piling up on that guy. Is that related?
Yeah. Recently there is I think Amin from Google gave a talk on hot interconnect about building the next generation AI network. So in that talk, he mentioned that with synchronized clocks, we can schedule the traffic ahead of time.
That's the word.
Avoid congestion. Yeah.
Thank you.
All right. Any more questions? All right. Hearing none.
We get a copy of the slides?
Yeah, slides will go on the wiki. Again, as long as Yuliang is going to share them with me, I will put them with the recording at the same time on the wiki. And I hope you know where to get the wiki, right? Just go timeappliances.com and get you to the wiki. And yeah, if there's no more question, we will see everyone on September 10th by a sorry, was there anything?
Sorry, go ahead.
Yeah, September 10th by a talk from Mason Marshall from NIST about the high stability single ion clock. And yeah, thank you again, Yuliang, for the informative presentation. We look forward for the SIGCOMM paper to be published, and perhaps maybe we'll bring you for another subsequent a presentation where you can then talk about more details after everything is released. And yeah, we'll see everyone in 2 weeks. All right. Thank you, everyone. Bye.